continue now.
Okay, thanks for coming to the talk. This is going to be on the research on resonant cantilever wings for monolithic micro-air vehicles. So first, let's talk about the question: could micro-air vehicles be smaller? First of all, how small are they today? This is a plot from a DARPA proposal that explained the sizes in grams versus the endurance time in minutes of various micro-air vehicle designs. At the time, this was in 2005, 10 years ago. The goal of the project was to make a micro-air vehicle which was less than 10 grams and could work for about 30 minutes. And since then, we've had some progress. So here's the Delphi Micro. It's a little bit lower there. You see at 3 grams, has a camera on it and a battery. These are robots that are flying with vision systems and with their own power supply autonomously. So this is 3 grams and less than 3 minutes. At least they're flying, they could fly autonomously. They also have typically remote controls to be able to operate them. Now, are we approaching some kind of a fundamental limit here? It looks like maybe we'll be able to get down to 1 gram. Maybe nature just doesn't let things fly if they're much smaller than that. Well, unfortunately, the pesky fruit fly would beg to differ, at its mass being on the order of 3.5 orders of magnitude smaller than even the smallest designs now. They can fly for quite a long time too. I'm not sure how long a fruit fly can actually hover for. I've seen studies that subjected it to hovering for at least 13 minutes. So it probably could do that for longer if it really had to. Now, the general approach to making micro-air vehicles is to use nature's flight approach to say, let's try to flap the same way that nature does and build this any way that we can. But the approach that I've taken here is different than that. I've said there's a lot of really smart people already doing that approach. Let's try a different approach, which is to use existing small-scale MEMS fabrication. How do we build things on tiny size scales? And see, can we kind of optimize this enough to generate enough force to make microchips fly? So with that in mind, this approach is a resonant piezoelectric curved cantilever fluid diode wing for mass-producible flying micro robots. To explain that a little bit in a little bit more detail, what's a fluid diode? It's analogous to an electrical diode, which allows current to flow through it only in one direction, so current can flow down but not up. Whereas a fluid diode, same kind of idea. It's easier for water to flow by it or air to flow by it in one direction than in the opposite direction. So if the cup's moving down here, it kind of resists the flow, and on the way back up, it allows the flow. Picture having a bowl, say, underwater. If you were to push this back and forth in the scooping direction, you're stopping a lot of airflow, whereas in the streamlined direction, it goes a bit more easily. So if you were to do this back and forth, even with a symmetric motion, which is a lot easier to actuate, you'd be able to get net force. How could we get a symmetric motion like this? Well, instead of taking a scoop and moving it up and down, what if we just open and close a scoop like we would get in a resonant curved cantilever? So by building a really thin strip of materials in a piezoelectric stack and putting different strains in them during fabrication, which happens in MEMS automatically. A lot of the time people try and design this out. By optimizing it, we can get really curved layers. Then applying an excitation to this at the resonant frequency, we can get quite large amplitudes. So believe it or not, the resonant mode shape of large amplitude curved cantilevers isn't known analytically in literature. So the first step was to try to extend the non-curved cantilever large amplitude resonant mode shape to curved cantilevers. You might ask, well, if we did this analytically, is it successful? Is this actually accurate? Does it model reality? The first thing it lets you do is predict what the resonant frequency modification should be to a cantilever because of curvature. And here's a prediction of that in green versus computational data using finite element methods by myself and another group. And you can see that it does seem to explain the trend from computational methods. Okay, so once we've got this flapping in this resonant shape, we want to figure out how much force it puts on air. For that, we used ANSYS. Here's a picture of ANSYS CFX flapping and demonstrating where the air goes. So the darker blue, the more quickly air is moving down, whereas red air is moving upwards. So you can see that it kind of gets the air going and then makes it avoid the wing on the way down, and on the way up, the air starts going this way and gets caught by the wing. That gives you an idea of why it is that this is generating force. So to figure out, to try and optimize this, we need to describe it. It's not really feasible to just do a new transient simulation on 180,000 mesh elements for every single type of design we want. So what we've done is used equivalent Reynolds number scaling, a technique that works all the time in static fluid mechanics, and come up with a way to describe transient fluid mechanics average results over many cycles using the same language. And if we do that, then we come up with a net drag coefficient that increases as we increase the Reynolds number along the x-axis here. Along the vertical axis, we've got flapping amplitude and increasing offset angle in the kind of slice out of the plane direction here. So the more red a number is, the better the net drag coefficient, meaning better force generation we get, other things equal. You can see this kind of plateaus if we go above an amplitude of about 40% of the length and above a Reynolds number of about 10,000. And the optimum angle is anywhere from 75 to 105 degrees. So you want to be close to 90-degree bending. In terms of dissipated power, things get more efficient in a similar way. We want to have sufficiently high amplitude. We want to have sufficiently high Reynolds number. But it's better to go higher and higher amplitude, higher and higher offset angle when it comes to dissipated power. Without having to dive into the math, it'd be nice to be able to explain these in terms of how efficient they are compared to nature. So fortunately, I've done that for you, so you don't have to go into the math of that if you don't want to. Compared to dragonfly wings, these curved cantilevers are definitely not as efficient. To produce the same force being just as big, it would take 7 times as much power. And versus fruit fly wings, it would take 11 times as much power to produce the same force while being just as big. That's not surprising. You'd expect that nature's a little bit more efficient with their kind of 3-dimensional, smart flapping motion than just like a not really that optimized opening and closing cantilever. But what might be surprising is that it's not that much worse than nature, only about an order of magnitude in terms of power dissipation. Now, does this actually lead to desirable robots? What we need to do is pick a robot design that uses these wings, then optimize it and examine the result. So here's an example of a robot design that uses this. We've got an H sort of structure, wings going out the side, 4 wings, a fuselage in the center with some control circuitry, supercapacitor power supply, and the top parts of the wings are silicon solar cells, while the bottom parts are piezoelectric quartz. Okay. Then, once we've got this, we can run it through a flow chart to say, knowing the input flapping shape and the stack structure, we can find out we can use the fluid mechanics results to figure out how much forces we're getting from this. Using the constraint that we're operating at resonance, we can pin down the size and frequency and then find out whether flight's actually possible. If it is, we can calculate some figures of merit and say how good is this compared to other designs. So I'm gonna draw your attention to 3 different designs. Here they are there. There's the large design, the medium design, and the small design. This is all to scale, so you probably have seen a TED Talk with the DARPA-funded Hummingbird Nano Air Vehicle. That's this in the background. There's a person's hand. This is a Dragonfly, a Penny, Harvard RoboBee, which is using the same kind of flapping structures as insects are. Currently, to date, it can lift